Okay, well, thank you very much for the invitation. The organizers asked me to speak about high precision evaluations of Feynman integrals involving elliptics and beyond. And they also knew that I'd speak about the quasi-periods and intersection numbers of modular forms. But what they didn't realize was I also would like permission to speak about high precision determinations of the areas of the event horizons of black holes, which if you told me I was going to speak about that a year ago when we met at Potsdam, I would have been rather surprised. Now, the subject is really very limited. I'm just talking about four-loop sunrise integrals with 5-unit internal masses, and those give Bessel moments that evaluate periods and quasi-periods of modular forms, levels, very important numbers, 6, 14, and 34, and weights up to 4. Now, when the external mass in this four-loop sunrise diagram is unity, we're talking about contributions to the magnetic moment of the electron at 4 loops. And Stefano and Laporta and I really understand what's going there. And thanks to my work with Vadim Zudlin and with David Roberts, we understand that what we're doing is meeting the periods and quasi-periods of a modular form of level 6. And what I'm going to do is change the mass of that external particle. And if I set it equal to the square root of -7, now we understand what that means, because we're talking the Minkowski norm of p squared would then be equal to -7. So I'm just evaluating a diagram in the spacelight region. Then we find periods and quasi-periods of a modular form of level 14. Absolutely astounding. And if we set it equal to the square root of 17 -4, is my pointer working, Jacob?
Yes,
Yeah,
I can see it.
Thank you. That's quite a small number, comfortably away from any of the singularities of this of the differential equation which is underlying this diagram. We also we get to level 34 and determine the areas of event horizons of black holes, which are obtained from compactifying a 10-dimensional supergravity theory. For the experts, it's a type 2b supergravity theory in 10 dimensions with n equals 2 supersymmetries. But to get a 4-dimensional black hole, to get from the unreal world of string theory in 10 dimensions to the real world of 4-dimensional space-time, we need to compactify. And the compactification is on a Calabi-Yau threefold with complex structure, and wonderful to relate, the Calabi-Yau equation associated with that variety is the same Calabi-Yau equation as for the 4-loop sunrise integral. Okay. So now let me see if I can get to the next page. So now I should, at the beginning of a talk, define the mathematical objects that I'm concerned with. And I've done this on a single slide here, and I've done it in a way that would be perfectly comprehensible if I was so fortunate to be invited to a seminar in Leonhard Euler's group in St. Petersburg in 1760. Because I'm going to talk about Bessel functions, the moments of Bessel functions. Now, we all know that it wasn't Bessel that defined the Bessel function. It was Daniel Bernoulli 282 years ago in 1738. I hope I got that calculation in 1738, who showed that the oscillations of a hanging chain are described by a Bessel function. We now call that J0. And then here, I see the continuation of that, the Bessel function for I0 for real arguments is J0 for imaginary arguments. I see here Bessel function I0. Now the solution to the Bessel's equation, there are two solutions. This is the one that's well behaved at the origin, and this is the one which has a logarithmic singularity at the origin and is very well behaved at infinity, falls off exponentially. So what this is a Feynman diagram. If I put these little numbers m and n equal to 0, then I have 5 exponentially falling Bessel functions. Those are the 5 propagators inside the diagram. I'm integrating x dx, which tells me that I'm in 2 dimensions. X is the proper time from one vertex of the this 2-vertex diagram to the other. And the dependence on the external momentum, z squared, is going to be a real number, can be positive or negative in the space-like or in the time-like or space-like regions. The Fourier transformation with respect to the external momentum brings in another Bessel function. So this is these I couldn't explain in St. Petersburg in the 18th century, the quantum field theory that produces this, but these are perfectly easy to define and nowadays numerically to evaluate one-dimensional integrals. Now, what about these parameters m and n? Well, we understand what m is. It's the number of lines that I've cut. If I change one of these propagator terms and by putting it on shell, then I get the other solution to the Bessel's equations. What about this n here? Well, n corresponds to differentiating with respect to this external momentum z. But to show you that, I need to introduce this second family of Bessel moments, where I've differentiated once to get the derivative of a Bessel function. The relationship here is I differentiate with respect to log z to turn m into n. But then if I differentiate twice, because the Bessel function satisfies a second order differential equation, then I get back to the m's but shifted. So we know that these satisfy differential equations. Not surprisingly, it's a 4th order Calabi-Yau differential equation that we have down here. So really we only need m and n, big M and big N, little n equals 0 and 1. Those 4 constants determine all of the higher derivatives. Okay, so those are the mathematical objects. But also, the heroes of this talk, a series of integers, very interesting integers. They enumerate something very important in lattice physics. But the first 3 of them are 1, 5, and 45. And they're generated by taking the 5th power of Daniel Bernoulli's Bessel function. He knew its expansion coefficients, they just involve x, coefficient of x to the 2n is 1 over 4 to the n times the square of factorial n. This is very, very convergent series. And so I take the 5th power of this, extract, take the power of x to the 2n, extract the powers of 2 and factorials, and define these integers. So what are these integers? I mean, they've come from Bessel functions, but what have they got to do with the Feynman diagrams? Well, you can see that the definition I've given gives this explicit formula, which is the number of self-returning walks of length 2n on a 4-dimensional diamond lattice, and that relates deeply to the condensed matter physics, and this is 4-dimensional condensed matter that I worked with John Borwein and with Larry Glasser. Of course, we would never use that formula when we look for a recursive definition. I give here the recursive definition in its most economical form that John Borwein and I derived 15 years ago. I define here 4 polynomials. Now they're quartic polynomials. They're actually quadratic polynomials in t squared. T is just a variable of that polynomial. And this is the recursion relation for those numbers. If I know 3 of them, I can find the 4th. It's a 3rd order recurrence relation. And in here are just the integers. You see, I just substitute n and k down here. So it's a 3rd order recurrence relation with degree 4, powers of m to the 4 down there. But the corresponding differential equation, you just shift degree and order. We have a 4th order Calabi-Yau differential equation here. It's 4th order because it involves now 4th derivatives, and it's of degree 3 because it only involves x to the power 3. And you see down here. So this Calabi-Yau differential equation is the thing that the string theorists were interested in. And you can see that it's a fourth order differential equation, has four solutions. If I'm at some arbitrary point x and I want to completely specify everything in the neighborhood of that point x, I need 16 numbers, the 16 periods of this Calabi-Yau differential equation at the point x. Okay. Now the map to Feynman diagrams is very simple. Their Calabi-Yau x is equal to 1 over the square of the Minkowski square of the momentum of the external particle. And the fourth order differential equation for Feynman diagrams comes from just the same polynomials down here, the same fourth order polynomials, involves powers of z squared, but the sunrise diagram itself with no cut lines satisfies the inhomogeneous differential equation. And here the right hand side of this equation is factorial 5. So what we've got down here is the Picard-Fuchs equations for the sunrise diagram, this external mass with 0, 1, or 2 lines cut. We can't cut more than that because the Bessel functions don't let us. So this is why we only need, even if we want to know all of the derivatives, you want to expand about this point, as people are doing in practical calculations. We just need 4 of these. We need, for a given value of m, we need m at 0, n at 0, m with 1 there and 1 there. And I give an example of how a higher derivative would occur. And so suppose that I know these 4 derivatives and I want to calculate higher derivatives, then I have to divide by this thing, which is cubic, because it's a cubic in z. So I have to divide by this cubic in z squared. I have to divide by these 6 factors. And I'm going to end up with horrible numbers when I do that. But now I tell you a very nice feature about this special point. Z is equal to the square root of -7. You can do this calculation in your head. Right, I want to evaluate this as square root of -7. Well, I have 1 plus 7, I have 9 plus 7, I have 25 plus 7, and I think you can do that in your head and work out that I have the 12th power of 2. So it's going to be very, very simple to develop these expansions at this point. Now, an even more remarkable trick is when the external mass is square root of 17 minus 4. This is a unit of the quadratic number field Q square root of 17. It has unit norm. If you multiply it by its reciprocal, you get its conjugate, you get -1. Conjugate just means changing the sign of the square root of 17. So we're going to have to divide by the norm of D if we're at this point. And now, there's a wonderful trick. The norm of a rational function of u is the function times the conjugated function. And we can work out what the norm of this is, right? So down here, I've got 1 minus u. The norm of that will involve 5 squared minus 17, and I get 8. Now, I could do that for you for all of those, but now I tell you that I can immediately deduce that the norm of the number by which I have to divide in the quadratic number field is minus the 25th power of 2, a rather memorable number because we've got 10 fingers. The 25th power of 2 has a rather nice feature, 33554432. And that comes from the splendid quintic identity that this mass satisfies this quintic equation. And that's where the 25 comes from, because I have 3 powers of 2 from the norm of this, and I have 22, and I have 22 powers of 2 from the norm of this, and I have a minus sign from here. So it's hard to imagine better regular points of this differential equation. Of course, we know the really important point for the mass of the electron is z equals 1, but that's a singular point of the differential equation. These guys have discovered beautiful mathematics happening at a regular point of this 4th order Calabi-Yau equation. And the discoveries were by Philip Candelas, Zenia de la Ossa, Mohammed Elmi, and Duca van Straten. And they were working entirely on the Calabi-Yau side. Being good string theorists, they were totally oblivious to Feynman integrals. They never understood them. They've been told in their early days as string theorists that you should never waste your time evaluating the Feynman integrals because to do with the quantum field theory of point particles, and the world is really made of silly little bits of string. So they were completely oblivious of the machinery which we had developed at the singular point of this differential equation. Now, what they found is that these points down the Calabi-Yau side, x equals -7, and 33 plus 8 times the square root of 17, were very interesting arguments for the analytic continuation of the solution to the Calabi-Yau differential equation. They had to do analytic continuation because the radius of convergence is only 1/25. We know physically there's a branch point at z equals 5. You can't, if you have a particle of mass 5, it can decay into 5-unit mass particles. So we knew, and that meant that I had to do some very slow and tedious Runge-Kutta integration. Of course, we don't have to do that. I was immediately able to transform, when I heard just this value, they just said x equals -1/7 is interesting, immediately transform all of their things to the Feynman diagram side. So now I go to that, and I go through the next 2 slides very quickly, relatively quickly, because I've talked about them extensively at previous conferences. But if you haven't heard this before, the magnetic moment of the electron has contributions from the on-shell sunrise diagram. So that's M00, and on-shell means external mass is equal to unity, 5 propagators. Now, of course, this has this wonderful representation in terms of the Feynman or Schwinger parameters that Karen was talking about yesterday. And here's a second semantic polynomial, and involves 5 parameters, because there are 5 internal lines, edges as Karen would call them. It has this wonderful form down here. If I take out some powers of x's down here, I take the sum of the 5 parameters times the sum of the reciprocal of the 5 parameters and subtract z squared. You can see why, as long as z squared is less than 5, this is a perfectly well-defined integral. It's only when all of these x's become equal to 1 and z that we find a singularity. Now, in Stefano's calculation, what about these m's and these n's that I'm talking about? How many of these did he actually need? Well, at this singular point, first of all, we have to have the uncut diagram. We can only cut 1 line at this point. We can't cut 2 because this Bessel function, then I'll end up with 3 Bessel functions killing whose exponential behavior kills off the remaining 2 propagators. So I've only got these 2 things to look at. And you might think that I need for the diagram with 1 cut edge, I would need 4 numbers, but I don't. I only need 2 numbers, because at this singular point we see zeta values appearing, and the recurrence relation that became singular at that point also eliminates the other values of m. So we're only left with 4 numbers, and these 4 numbers have an intersection number. They satisfy a quadratic relation, which I discovered. So the sunrise diagram on shell, this is a second differential with respect to external momentum. This is with 1 line cut. This is with 1 line cut on a second differential. The determinant of this matrix is a multiple of zeta 4. Underlying this is modularity. And here we have a very explicit construction of the modular form. I take the Dedekind eta value. Now, tau is just like it was in the previous talks on modular forms. It's in the upper half of the plane. Q is the expansion parameter, exponential of 2 pi I tau. And this, with this marvelous factor of q to the 1/24, is a modular form. And of course, we want things which have expansions in powers of q. We don't want these 1/q to the 24. Well, what you do, eta of n, I'm going to call eta of n tau, but I take eta of tau, and eta of 2 tau, and eta of 3 tau, and eta of 6 tau. Each of these has weight 1/2. So I want to weight 4 modular form, I square it, and is it going to be okay? Well, can you do that sum 1 plus 2 plus 3 plus 6 times 2 is equal to 24. So this starts off like q. It's well behaved. It's a cusp form. It falls off exponentially fast in the upper half of the plane where q goes to 0. That's the modular form. But from work by Francis Brown and Dick Hayne, I know I also need a weakly holomorphic form, something with a singularity at at one of the cusps, something that you will not find in the textbooks, because it will be the integrals of that which provide the quasi-periods that, together with the periods, give us the intersection number. So here it is. I constructed it. It took a certain amount of ingenuity. I took this very well-known modular form and I multiplied it by this function of W, where W is an invariant of transformations of gamma 0 of 6. I don't know if you remember Stefan Weinziel's talk, and he talked about congruent subgroups. So down here, and this looks perfectly innocuous. I'm taking something that's very, very well behaved in the upper half of the plane, and I'm multiplying it by some of this Q expansion. But the price is that this W becomes 0 or infinity at 2 of the cusps. So it's a weakly holomorphic form. However, I've still got one cusp from which I can integrate. So the periods and quasi-periods, I take my modular form, I take my weakly holomorphic modular form, I integrate them from tau equals a half to I infinity, where they're perfectly well behaved. W is equal to 1 at tau equals a half and is equal to 3. And then I use a modular transformation. Do you remember yesterday's comments? I was saying, make sure you fully exploit modular invariance. And in the talk, in the second of the talks, we heard people very seriously exploiting modular invariance, but they were only exploiting SL2Z. Here there's a GL2Z, that is to say an integer matrix which doesn't have unit determinant. It's called an Atkin-Layler transformation, and it swaps cusps. And so when I operate it, what it does is it turns W into 3 upon W. So the integral I had to do from a cusp up to infinity, I can now do up to the fixed point of this transformation, which is 1 plus I of the square root of 3 upon 2, and then up to infinity. And then you see how I can calculate at the canonical Laporta rate of 10,000 digits a second. You know, the guys in Oxford can manage 50 digits a week, but we want, Stefano needed 20,000 digits of hundreds and hundreds of integrals to do his parallel PSLQ to make analytic evaluations of the Feynman integrals contributing to magnetic moment of the electron. So that's how we get this this efficiency. And here now is Laporta's intersection number. I take linear combinations of these diagrams, I remove factors of pi, and I get the periods of the modular form and the quasi-periods of the modular form associated by its weakly holomorphic partner. And David Roberts and I have, as you've heard in previous talks, have conjectured explicit by Roman Lee and by Babas, have conjectured explicit forms of all such quadratic relations on shelf, all loop sunrise diagrams, and Javier Frezin and Claude Zappa and Yang Dou Yu have proven our formulas up to 20 loops. They ran out of computing, they ran out of combinatoric computing power to prove our explicit one-line formulas. So now what I want to do is to go to this space-like case, right, p squared equals -7, which engages level 14. Now, on the Calabi-Yau side, what we need is a Frobenius basis. Now, remember that Y0 is the thing with these lattice counting integers as its coefficients, but it's only one of the solutions. It's the regular one at the origin. The others will involve first, second, and third powers of the logarithm of x. They're the singular ones. It's a fourth order differential equation, so we can stop down there. But we can take out the singular parts of these other solutions, and we're left with the regular things down here. This is what the Frobenius basis is. And these have expansions about x equals 0, perfectly regular, and the coefficients of them are rational numbers. And we can very readily find that. And these guys want to get to z equals the square root of -7, and they've got a real problem. because the radius and convergence of this series is 1 over 25. You already know that from physicists, but you can work it out yourself. Even if you just count it, if you work out how many self-returning walks there are and the walks get long enough, this number grows like 25 to the n. And I developed the asymptotic series that tells you that this function down here has a dilogarithmic singularity at x equals 25. Now, they don't want to go to x equals 25, they want to go to x equals -7, but that's outside the radius and convergence. So they had some very nasty, dirty work performed particularly inefficiently by Mathematica to do Runge-Kutta integration of this fourth-order differential equation. Because as quantum field theorists, we've got no such problems. They're merely evaluating a Feynman diagram with a perfectly well-defined non-singular point in the space-like region. And we have it as a one-dimensional integral. Underlying this are the modular forms. Now, it took me the best part of a day to identify the modular form. From hearing in the afternoon, for hearing in the morning before a seminar by Mishy Berinsky in Oxford that x equals -7 was interesting, I was able to find out that what they were doing were calculating, among other things, the periods of this modular form of weight 4 and level 14, which I've constructed out of eta functions. And its periods are critical values of the L function. The L function is just the Eichler integral from 0 to I is infinity, suitably normalized. And we know from conjectures by Deligny and Grothendieck, eminent luminaries, that the critical values of this L function are related to the periods of the algebraic variety that is inside is the denominator of our Feynman integral. So we expect, and the numbers relating these that are conjecturally rational, but you normally calculate them by evaluating the left and right hand side of the equation and finding the nearest rational number. In fact, it's been proven, at least in the on-shell case, that the exact relationship between this Feynman diagram, the space-like point, with one cut or with two cut lines give me the L function at 3 or 2, and by Eichler-Shimura theory, the value at the critical integer s equals 3 is related to that at 1 with this part squared, which keeps the transcendental weight correct. But what's really interesting down here is that I'm in an elliptic case. Gamma 0 of 6 has genus 0. There's no modular curve of conductor 6 on shell, but here there is an elliptic curve. And it's very easy to find the underlying elliptic curve. Now, we as physicists know that all elliptic curves are quartic. It's only mathematicians who like to write them as cubics, because we typically encounter quartics as 2 square roots coming from Chilean functions. And, now, to find this quartic, it's very good because we already know the modular, we should be writing this in the upper half of the plane. So what I've written down here is an eta quotient. This is not a Haupt module because we're in genus 1, but it's an invariant of gamma 0 of 14. It's got this very nice Q expansion. This is going to be the x of my cubic equation, elliptic equation. And what's the y? Well, I should differentiate x with respect to q. Well, I differentiate it with respect to log q. But hang on a second, when you differentiate a modular form, you increase its weight by 2. So if I just take this x, I've grissed out dx by dq, I've got to divide by some modular form of weight 2 to get a modular invariant and gamma 0 of 6. To make sure that my parameterization of the curve in the upper half of the plane has the correct modular invariance. And so I do that, and I evaluate that, and I only need to, you can do this by, derive this equation by hand. You only need to calculate up to here and up to here to find out that that's the elliptic curve. And of course, you can prove that's the elliptic curve because by modularity, this particular thing for 4 terms of the expansion constitutes a proof. You can verify it up to powers of q to the 1,000, but a mathematician will tell you you don't need to do that. An empirical determination like this that gives you a finite answer is a proof. Wonderful bit of combinatorics there. So the periods of this weight 2 modular form at level 14 are computable at lightning speed, not the 10,000 digits a second that Stefano and I want to know about, but the 100,000 digits a second that Gauss's process of the arithmetic geometric mean gives you. Here's this very interesting arithmetic geometric mean. I take 2 pi and multiply by the arithmetic geometric mean of these, and I get the 2 periods. Now, I've only got one L function. It's the subject of the Birch-Swinnerton and Dyer conjecture at the center of the critical strip for a weight 2 modular form. And this particular case, the Birch-Swinnerton and Dyer conjecture is proven. And one of the periods down here, let's call it the real period. I put plus and minus down here. The complex period that I get by taking these, taking this imaginary part with the minus sign, this defines a J invariant, and the J invariant of this curve is this. So you can find it in the dictionaries of people that like to write cubic equations just by looking for something with that J invariant. But these elliptic integrals are determined by Feynman diagrams. Now remember that we've got to cut one line or two lines, and they're determined by this and the first derivative with respect to the external mass before the external momentum, before we put p squared is equal to -7. One way of saying that is that we now know how to calculate these Feynman diagrams to lightning speed because we know how to calculate arithmetic geometric means. Now this is the stage that I was at in December when I met Eric Panzer in Padova, and he asked me a question that really shook me. He said, can you really derive all 16 Calabi-Yau periods from Feynman integrals? It looks impossible. I've only got 8 Feynman integrals I can talk about. And yes, I can, but only at these very special regular points. And so I can now tell you in the affirmative, I have evaluated all of them, all 16 at these points and others at other points. And in fact, 6 of them are enough because there are 2 intersection numbers. We've heard a lot about intersection numbers. So the 16 Calabi-Yau periods are analytic continuations of the derivatives. And the quasi periods associated with the modular form, they're just the complete elliptic integrals involve the third derivative, sorry, this is the value of the first derivative, the second derivative down here. And of course, Legendre told us all that time ago what the intersection number is. We just take the matrix of periods and quasi-periods of modular form associated with the elliptic integral, and here now is the intersection number. So that's got rid of one of my Feynman diagrams. And of course, what I'm expecting is to be able to do the same thing for the section number of the periods and quasi-periods of the weight 4 modular form, which will involve my 4th derivative. And it didn't take me very long to discover that this is the generalization of the Laporta matrix on shell at level 40, level 6 to level 14. Okay. And indeed, I can evaluate these as Eichler integrals of weakly holomorphic modular forms. So looking at the time down here, I can quickly tell you what happens at level 14. Again, I have 8 Feynman integrals. They satisfy 2 quadratic relations. The external mass is this. But now I need a Dirichlet character. Can you see how the whole machinery, which we've heard about in previous talks, which is for practical calculations with Feynman diagrams, is coming into play? Dirichlet character is a trivial one that tells me that if p is not equal to 17, the character is plus or minus 1 according as whether or not 17 is a square or is not a square modulo p, or Gauss tells me that that's the same as saying whether p is or not a square modulo 17. And there are 12 cusp forms. There were 4 cusp forms I'm sorry, this is a mistake. This is a very big mistake. We're at level 34 here. That's a very big mistake. So we're at level 34 here. There were four cusp forms, so already quite a complicated problem. Here I have 12 cusp forms, but I identified a pair of new forms, things that cannot be derived from lower levels like 2 and 17, whose Fourier coefficients are in a different number field. They're Gaussian integers, in other words, a plus ib when a and b are integers, and the two modular forms are related by complex conjugation. So the L values of these critical L values we're looking at are the analytic continuation of this L series, which we know for a modular form is given by an Eulerian product over primes, but here with this character appearing. And so we only need to know, and Paris-Pay will tell us for the first, all the primes up to 1 million or whatever it is, what these Gaussian integers are, and very beautifully, if p is a square modulo p, this is a real integer, and if it's not a square modulo p, it's I times an integer, and only at the very special prime that divides the conductor down here do I have a truly complex number. So I can evaluate, right, the Feynman diagrams that are involved, and because of modularity of the L functions, and find, but now the linear conjectures tells me that these things should be related if these are, as I can, the Calabi-Yau periods should have numbers, not rational numbers now, but numbers, biquadratic numbers in square root of 17 and the square root of -1. And so these are the numbers I determined empirically. It doesn't take very much PSLQ to find numbers like 13 and 1. And what that means is that I've now evaluated two of my Feynman integrals in a highly efficient way, 10,000 digits in a few seconds. And also, down here at weight 2, I expect to have the periods and quasi-periods of a elliptic curve. And here I've written it in a very nice cubic form. It took quite a while to write it in this form. If u is equal to z, these are at the zeros of this polynomial, which factorizes in this quadratic number field, telling me that there are singular points of the differential equation at z equals plus or minus 5 and z equals plus or minus 3. Here are the real and imaginary periods. I'm just doing the same thing before. Here I have 100,000 digits a second. And here is the empirical relations that I have between the easily calculated elliptic integrals and the relatively easily calculated Feynman diagrams. And now in here we have coefficients which are integers in a quadratic number field. These would look pretty horrible if I start expanding out these factors, but we have a unique factorization domain. And here's Legendre's condition. So, looking at time, I'm bang on schedule. All I had to do to solve this problem was to find the quasi-period associated. Here are the periods of the modular form, and here's my determinant of the quasi-period that satisfies this intersection number. So what has it got to do with black holes? Feynman integrals determine the areas of the event horizons of black holes, which are specified by charges. These black holes come from, as I said, from taking a type 2B 10-dimensional supergravity theory, two supersymmetries, compactifying it on a Calabi-Yau threefold with complex structure, the Calabi-Yau threefold associated with the second semantic polynomial of the sunrise diagram. Wonderful to relate. And the area of the black hole that they get, specified by these charges, it's multiplied by 34 pi, which looks like a pretty sensible number to multiply by at level 34. And there's this number v. Now this number v comes from these critical L values. But the way it appeared in their thing was absolutely horrible because they didn't know about Feynman integrals, you know. So they had, when they expressed the number v, they had all sorts of nasty factors of I and pi and square root of 17 and goodness knows what. But in fact, this v is just a ratio of two Feynman integrals. So I take the sunrise diagram, I put the mass equal to the square root of 17 minus 4. I cut two internal lines and one internal line to get a number of transcendental weight 0. I jolly well better multiply by pi. So there are only two numbers that you have to calculate if you know about Feynman diagrams. You can calculate these to thousands of digits of accuracy, but you only need a couple of digits to work out that this number here is 4. And this number 34, I take no responsibility for. These are the experts down here, they tell me. Now, what do you think happens when I go to the spacelight point? Well, I don't think it takes too much ingenuity to know that this number turns into 14. And so, and all down here, I go to p squared equals -7. I put u is equal to the square root of -7 down here. And so I had one number to calculate in that particular case, and it turned out to be 2. Now, what I was able to do, as well as show how beautiful these areas are, was to identify 6 constants they lack. There are 48 constants around down here because there's 4 solutions up to 3rd derivative, and the neighborhoods of these points, and they were lacking 6 of these constants. And I was able to, I knew what they didn't know. What they didn't know was that Dick Hayne and Francis Brown identified these numbers from the permanence of the matrices of Feynman integrals. Feynman integrals to me, whose determinants goes the intersection numbers. So I knew what numbers they were missing. They're really only missing 4 of them because the numbers they were missing at plus the square root of 17 were related to those at minus the square root of 17, though they weren't able to prove that. And in this work, I was greatly aided by my work with Kevin Akers on Rademacher sums, because the Rademacher sums are what determine the permanence. When I have a matrix, when I say down here, of course, I can add any multiple of this and still get the same determinant. But that special number down there, that is relevant for the permanence of this matrix, which is where I take the plus sign down there, then it really matters. And so there's quite a lot of theory underlying 81 and similarly for the level 14 case. So I conclude, Xenia and Philip and Mohammed and Duco made this absolutely amazing discovery. It's totally theirs. At the level of mathematics, that a Calabi-Yau equation, which we already knew gave periods of a level 6 modular form at a singular point, also gives periods of modular forms of levels 14 and 34 at regular points of that equation. I mean, something which I don't think, it ought to have surprised the mathematicians. It absolutely astonished Stefano and me. But you see, Laporta and I, and along with David Robertson and Anton Mellet and Yajun Zhao, we completely mastered the mathematics of the level 6 case because, you know, this is a matter of real importance in quantum field theory on the Feynman side. So I was in this happy position of being able to bring the expertise from quantum field theory to bear on unsolved Calabi-Yau problems at levels 14 and 13 from the string theorists. And the 48 constants that they wanted are completely determined by my 16 Feynman integrals, which satisfy 4 quadratic relations. And then, to honor my promise to the organizers to talk about high precision, then in a space of probably, I'd like to say a few minutes, but one of these might have even taken an hour. I computed all 16 of these Feynman integrals to 10,000 digits, just using series expansions. Because my expansion parameters, this was the expansion parameter for the periods and quasi-periods at level 14. And at level 34, I used a mixed approach because here, down here, we're very close to x equals 0 if we take the minus sign down here. Remember, the expansion parameter is really 25x, but 25 times 33 minus 8 times square root of 17 is a nice small expansion parameter. And now I conclude, thanking you for your attention, with a sentence that I truly did not expect to communicate at a conference of this kind, namely that 2 ratios of Feynman integrals determine the areas of the event horizons of black holes from compactification of 10-dimensional supergravity. And thank you very much for your attention.
Thank you, David. We have time for a couple questions. Please raise your hand. Okay, well, I don't see any questions. Why don't we thank David once more, and ready for the second talk of the session. Thank you, David. Okay, our second speaker this afternoon is Matija Tepuskovich, who will tell us about motivic coaction and cohomology with twisted coefficients. Can you share your screen?